Here?
Yeah.
So first of all, I would like to apologize. So I had jet lag. I just came out from vacation, so I could basically say everything. Please forget about it. And so this is my variable index. So I will be talking about this topic of GPU-friendly networks, which is kind of the situation in research and corporate, and then we just briefly touch this GPU-directed delay thing and some perspective on the future. And so, yeah, this is the thing on which I'm most interested in. So, the problem of scaling. I was interested in this topic way before the GPUs appeared, but now that the GPUs are here and accelerator in general, I feel like the scaling problem is the most interesting one. I try to capture the problem with these few features. So yeah, I see the scaling problem as a wall somehow. And some people, especially researchers, try to climb up on this wall. And the reason for the wall is that you have a large simulation, and you have a lot of computing nodes, and you want to keep the simulation size fixed, and you want to split the computation on as many nodes as possible. And eventually, the amount of computation in a single node shrinks with a higher power than the network, which this thing has to do with the geometry or the topology of our space, which is three-dimensional, or four-dimensional in other physical problems. And so, you start seeing this problem, this scaling problem around hundreds or thousands of GPUs today. And there are a number of different reasons. There can be a bug somewhere, there can be poor coding, and there can be overheads. And I'm most interested in this overheads as far as it regards GPU and network interaction. Of course, even optimized applications, they sooner or later bang against this wall. My activity in the last year is more removing these walls, or moving these walls farther away. And so these GPU-friendly networks, this is a project I was somehow leading before joining NVIDIA. So this is a network interface card developed in 2012, 2011. This is based on FPGA. FPGA is I don't know how many of you are familiar with that. It's a hardware component which is programmable. So you don't need to do a VLSI chip from scratch. You change the slight programming. You design a piece of program which is converted in hardware, and you somehow flash this program inside that chip. You can enable new features basically. Using this infrastructure, we were able to add GPU peer-to-peer support in Fermi, which is the GPU previous to Kepler. Okay, so basically, Fermi was the first GPU to get this peer-to-peer capability, and we were able to transform this network card, which is this card we designed this card, and to make as if this card was a GPU, right? So you plug this card in the system, and another GPU is able to offer its services to this network. So today is, of course, we call this GPU directed DNA, but actually this system uses a different protocol, which is something which is hardware protocol embedded in all NVIDIA GPUs, which is called NVIDIA peer-to-peer. And so with this technique, we were able to reach 7 microsecond latency in 2011, November 2011. Eventually, we added NVIDIA peer-to-peer, but also GPU directed DNA, which is slightly different. And so another interesting point of this technology is that you can use this technology to interface GPU with third-party devices eventually open a new kind, extend this technique to other problems like astronomy. You can interface a GPU with a radio telescope or an optical telescope and feed the data directly out of the GPU. Or in energy physics, like there's a project now ongoing to extend this technology to particle accelerator detectors at CERN. Yeah. These are plots done 3 years ago, 2 years ago. Yeah, nothing very interesting today. This was a project. Actually, I proposed this thing to NVIDIA 2 years ago. Yeah. Then, there are GPU cards with a PLX switch inside, 2 GPUs. Yeah, there are dual GPU card. And the idea was to, hey, why don't we get rid of one GPU and use the free space to add a network. Right? So that would be like a Frankenstein card, where it is alpha GPU and alpha network card. So that would be mock-up. It's failing. There are other interesting research projects in the area. There is Pitch 2 in Tsukuba, where they developed this card, which is actually striking similar to APIC. It's like a different topology, and they're doing quite well, I believe. There is also some other, programming models like GIGAS, Global GPU Addressing Space, proposed by Heidelberg University Group. And I believe, yeah, they are both going. There's an ongoing effort toward the right direction. And then there was the project where I was involved mostly I've been involved in the last 1 year and a half. So we started in February of 2013 working on the prototype of GPU vector domain together with Mellanox and DK's group. So we made the first prototype, which DK presented at GTC 2013, based on, I believe, MVAPICH 2 1.9. And then there was a rework, basically needed for some constraint related to the OFED software requirements. And this work has been completed by December 2013, and I believe the first Mellanox OFED 2.1 was already available in January of this year. OpenMPI and MVAPICH 2 support for this OFED 2.1 right away. And yeah, so the problem with GPU vector domain is that it's not a free lunch. Okay? So it gives you an ability, but there are a number of limitations around it. So it's not always fair. So here, this is actually it's a slide by Decay many months ago, where I'm trying to. Is there a pointer? Yeah, this one here. So you see here. So when you use the red line is the usual approach when you use GPU copy data technical, is what we call pipeline staging. And then the red line was using the black line was using GPU DNA. You see that it's improved by using GPU DNA. But after, if you look at the bandwidth, you see the two effects. So after a certain message size, the GPU DNA is not giving you a benefit. Also, on the bandwidth, you see that there is a bandwidth cap here around 100 megabytes. That was on Sandwich. At that time, we were quite surprised. You don't know if it is the GPU, you don't know if it is the connection, the Ethernet card, if it was the system. Eventually, we discovered it is the system, the Sandwich limitation related to the purity of traffic. So inside Sandy Bridge, there is an indentation somewhere where two PCI Express devices are not allowed to exchange data maximum speed. So somehow there is every other megabyte limit. This limit has been lifted in Ivy Bridge, but it's still there, as I will show you. And so eventually you get 5 to 3 Mbps, 70% less latency, but you still have this crossover behavior. These are animations. And this is basically what you get on Ivy Bridge. So again, there is a threshold now because Ivy Bridge is much better. You see the bandwidth cap is a bit over the 3 gigabytes per second, but it's still there. And again, thanks to this increased throughput, even the latency crossover as we move away from 8 to 16K, it's closer to 156 kilobytes. But it's still there. So this means that you cannot always use GPU. If you have to move 1 megabyte of data, probably you should avoid using GPU. So somewhere in the middle where API is the right place to do that, has to make the right choice. So I'm transferring 1 megabyte. Should I use GPU or not? MPI is the right place to do that. And it is so because we have GPU-aware MPI. So, and this was the situation that the HPC, again, this is a slide. So we were roughly here in HPC 2014, a few months ago, and from there, we worked together. As the case showed today, there are 2 additional data paths. So it's a way to use movement to data movement, and I show you shortly. And this what is called your fast copy now is called GDR copy library, which gives you a nice advantage. But I mean, in general, what we have been working on is restoring here. So previous to this new 2.0 release, GPU RDNA were disabling eager protocol and using rendezvous protocol. I don't know how many of you are familiar with rendezvous eager. So there are techniques to efficiently move data around, where, especially in the point-to-point MPI primitives. So yeah, this is a short explanation of what eager is, but probably it's not very interesting to you. The point is that the point I want to make here is that there are clever ways to use what you have on your platform, right? So in this case, I have a very low latency device which is able to transfer data from here to here. But I can also use it to transfer data inside. Right? I can use an InfiniBand card as a powerful copy engine, very low latency copy engine. And then the second approach is this GDR copy library is an abuse case for technology which is meant for third-party devices. So the GPU is exposing data from the PCI Express bus, and so I said, well, why the CPU can use this data path as well? So we quickly produce a new library, and device driver, and basically, in this case, the data path is one where the data comes here on the CPU, and instead of using the network card to do the copy on the GPU memory, it's the CPU which is doing, and then copy operation from here to there. Again, even this approach has some limitations. as always. So it's zero latency because it's a copy given by the CPU. For instance, device to host coming from GPU memory to host memory is very low for particular reasons, for hardware reasons. It's 20 or 30 megabytes per second, it's incredibly low. So, but it's very effective on the other way. So the other direction is host device, host memory, GPU memory, to get up to 6 gigabytes per second on average. But again, it's sensitive to the speed of the CPU, the performance of the CPU, and there are also some uniform memory architecture effects. For instance, if you try to copy from the copying process is on a socket, and the GPU, for instance, is on another socket, you can see how the bandwidth. And this library is coming soon on this GitHub repository. I'm sorting out the legal framework for that. And this is a test I did a couple of months ago, probably. And you see this is 3.1, and now it's down to 2 point something. Yeah, this is where already covered. So, yeah, I would like to spend the last few minutes, I don't know, 5 minutes, probably, 10. 50, oh, it's plenty of time. So this slide has been stolen from a deck where it's Jets. One Jets deck here. So anyway, it's unreadable. I don't know why. It doesn't even work on Mac. This one is showing that the problem with scaling is that most of the computation when you scale, when you have more GPUs, goes down nicely in this case. But there is one part which is not scaling at all, which is the communication part. Right? And what can we do about that? So if you go to the profiler, this is the CUDA profiler for NVIDIA GPU. Nicely, you can kind of see where the problem is. So you have some computation here on the GPU, and actually a number of computation here back to back. And then there is some API communication, probably that you're communicating data which has been calculated here, is good occurrence. And then there is some other computation here, probably working on the data which has been communicated, or also this communication could be in progress, overlap with this computation here, because they are computing something which is not related to what they are communicating. But the good point is that we see here the CPU is mostly sitting idle, while here it has to react quickly, very quickly, say, to the fact that the computation has been done and issue the communication part. So let's say this is a fairly optimized GPU code where most of the code is on the GPU side. So this is pretty unusual. And anyway, this shows you that the CPU, so we are not using the CPU, but for a few spots where we actually need a very fast CPU. So we need a very fast CPU here, while most of the time it's inside. Which is kind of a waste. And it's not only a waste, by the way, because if you think, so here I'm just saying what I was saying before, so that the CPU is only the management side, so it's waiting for a kernel to launch a communication, it's waiting for a communication to launch a kernel, and it's actually doing all most of the time. And the problem with that is that if you fast forward to a few months in the future, where we start using R as a CPU on our clusters, probably, you will have a problem. Because R is not as reactive or as fast as a Xeon is. So working in that area, I showed you before, is probably going to help you know, a hard-based cluster. So the point is that when you have a slow CPU, it's possible that when you are on hundreds of thousands of GPU range, it will be a bottleneck, even though it's not doing anything at all. Only because it's not reactive enough. So the idea that we are working on now is somehow, yeah, you know, this is the typical, I think, structure of the extensive computation code, or the domain composition code, where this is one-dimensional or two-dimensional. So you have some hello computation, and you need to do some computation. Probably you have two L's. Then you have a path computation, which can progress independently of the hello computation. Then you have to wrap up everything at a certain point to calculate some intensive quantity, and you have to synchronize at the end. But you have many synchronization points because you have to wait for everything to launch the energy calculation, and you know, and you have to create somehow a synchronization data structure, which in our case is, in the case of CUDA, is the stream. So as you can see on the right hand side, this is the zoom inside the GPU. So the GPU, from the point of view of as an accelerator, as a front-end part and a compute part. The front-end part, you can say, is a kind of a command engine. So commands come in from the software. This is hardware. So there are some hardware queues where commands are injected, and then the commands are fetched by the execution unit, the dispatch unit, where pull commands from here to the compute engines, right? So the point is, this object could do something else also. So here we have a compute kernel, and then we have a communication, right? So what if the end of the kernel could trigger the send, the network send, independently? So what if this guy here, the other block here, could trigger the send operation on the network? Okay? So in that case, the CPU would not be needed at all, right? And so that is a path that we are working on. Another thing which is going to happen in the near future is that new I/O interfaces will be introduced. For instance, for NVIDIA, there is this NVLink 1.0 in Pascal. So when Pascal will be out, there will be this new link, which is something different from. So there will be PCI, you know, there will be still a PCI Express. But then there will be also these 4 NVLinks. So these 4 NVLinks, you can think of them as 4 huge pipes coming out of the GPU, and you can attach these pipes to other devices. So in the case of IBM, probably there will be the CPU by IBM will have a corresponding pipe. So there can be a direct interconnection between the GPU and the CPU. And also among GPUs, it will be possible to link 2 GPUs together by using MVAPICH. And the link will be very low latency and high bandwidth. And you know, this is what is called on our websites. And I look forward to the day where there will be also a network, an NVLink attached network. Why not? So actually, my summary. So summarizing, I would say that for GPU heterogeneity and peer-to-peer in general, we see that there are some limitations. I don't know how Azure will be, but I don't think that Azure will solve all the problems. So we will still needing a very efficient MPI to choose different data paths in the future. Because there will still be limitations in our hardware platforms. And by the way, I have time to show you something. So this is what you get when you have two nodes connected by connect ID cards, and you do a GPU to GPU transactions. This is a low-level InfiniBand verbs benchmark. And you see that due to the ID bridge limitation, you can only get up to 3.4 gigabytes per second. If you use the boost clock in the K40, only the K40 has boost clock, you can get up to 3.7. But this is actually telling us something about the kind of problem they have here. But if you use the, for instance, these are a few of the problems you could meet when you have your feedback card in one Xeon socket and you have the GPU on the other one. You see that there is 1 gigabyte of bandwidth available in one direction and only 250 megabytes in the other direction, which is kind of surprising. And I would just say that today, the best platform for doing peer-to-peer is one with a PCI Express chip switch, like this one with PLX. So if you care a lot about GPU directed domain, you should probably consider a PLX-based architecture, where you can get 5.8 gigabytes per second of GPU directed domain bandwidth and reasonable latency. So if we go back to the summary, so still in the future we'll have these multiple data paths, different topologies, eventually NVLink, and we will need some kind of software to manage all, to do the right choice at runtime. It will not be possible to do that at compile time. It will be a runtime decision to use the right data path. And we are working on ways to reduce the overheads, like using the GPU as a scheduler also for the network. And that's all. Yes.
Any questions for everybody?
Thanks, everyone.